Good afternoon, honorable guests, distinguished professors, and members of the audience. My name is Raymond Ho, and they are my team members, Yeung K, Apollo, and Anson. And we are from GT College. When people ask me, what are your thoughts about prime numbers? Well, I can tell you that they are really my prime concern at this moment, because I'm doing a research on the classification of prime numbers by prime number trees. And this is the basic rundown for today, and so let's begin. Great. Maybe. First, I'm going to start with the traditional classification, which is the system which people usually adopt to. It is without doubt that Erdos-Selvidge's classification is the system which is quite a pioneer in the classification of prime numbers. For example, 2, 3, and 5 belongs to class 1, and 13, 19, and 22 belongs to class 2, etc., etc. But there's no regulation between the prime numbers. And so, the classification methods has some minor drawbacks to it. First, it classifies prime numbers according to its classes, making it class-dependent. Second, it contains infinite classes, which have an infinite number of primes. And together with the lack of regulation in its appearing primes, it makes things a bit too complicated. That's why we've tried using a new method of approaching the classification: the prime number trees, also known as PN trees. PN trees work under a scheme called SOUIPMT, or the SO scheme, where it basically says that we multiply 10 to an old prime number and we attach 1, 3, 7, or 9 to it. This diagram is the prime number tree of 2. You can see that the 2 is the first digit and the starting prime number. So let's apply the SO scheme here. By the SO scheme, we multiply 10 to number 2, and we have 21, 23, 27, and 29. 21 and 27 are not included because they are composite, while only 23 and 29 remains. Going on, we also use the SO scheme on 23, so we are only left with 233 because the rest are composite. We continue until the last number cannot generate any more primes by the SO scheme. The same goes on for 29 and all the other PN trees. You may note that there are finite numbers found in the prime number trees. Now, I'm going to introduce you the concept of the fundamental prime numbers and the tail prime numbers. The fundamental prime number is the first prime number in the diagram, which is number 2 here, and it cannot be generated by the SO scheme. The tail prime number is the prime number that cannot generate any more prime numbers via the SO scheme, and it may be 2, 3, 3, 3, 3. So if we attach 1, 3, 7, or 9 to 2, 3, 9, 3, it is all composite. Therefore, it's a tail prime number. Branches is a term that we use to describe the length of our PN trees. We define PN tree branch with square brackets starting with the fundamental prime number, P, separated by a semicolon, and then followed by digits D1 to Dn to be our prime number tree branch. It is a short form of writing the PNs, which we apply to this PN tree of 2. For example, the PN tree of 2 has 6 branches, and the PN tree branches give an elegant shorthand of the prime numbers in the PN trees, fully describing them and summarizing it effectively. For your reference, this is the prime number tree of 3. It illustrates similar features to the PN tree of 2, and you can find other PN trees in our appendix. There's one interesting case that I want to show you here. We have found out that for this fundamental prime number 89, no more prime numbers can be generated by the SO scheme, making it both a fundamental and tail prime number, isolating itself with the prime number world. Because it is so lonely here, so we nicknamed it the alone prime number. There are some further examples of alone prime numbers below, like 107 and 167. Moreover, our PN trees give a complete classification of all prime numbers, because all the prime numbers are either a fundamental prime number or a number generated by the SO scheme. Besides, every single prime number is unique in our P entries. They belong to only one P entry only, and the P entries don't intersect. They're similar to our concept of a family, because although we are alike in resemblance, but we're still unique in one way or another. The length of a P entry is defined as the number of primes in the longest prime number tree branch. It equals to n plus 1. The length of the P entry of 2 is 8. We have worked out more than 300 P entries, and they are all finite in length. We hence deduce that the length of P entries are all finite. However, after a long and tiring investigation, we still cannot prove that no prime number tree is with infinite length. But in this tunnel of darkness, there's light, and light is just over the next few slides of our PowerPoint. In order to prove this conjecture, we have moved into the number systems with a lower base to investigate. We start from a fundamental prime number. The following prime number is generated by multiplying it by 2, followed by the addition of 1, and it remains prime. For example, the binary prime number tree of 2 is shown, where 101111 is equal to the 47 in the decimal system. Why do we stop here? Because the next number would be 95, and hence 47 would be our tail prime number in this system. In general, for any fundamental binary prime number p greater than 2, by attaching p minus 1 ones to its right-hand side, this number can be proven to be composite by Fermat's little theorem. We have some comments about the binary P entries, where firstly, there are only one branch in each P entry. Secondly, P entries can be used as an identification of binary prime numbers. And lastly, it contributes in digital cryptology by using P entry to generate codes. After binary, we have increased the base to 3 to approach decimal. We are getting closer and closer, step by step. I will now analyze the properties of lengthening the ternary prime numbers. First, we let p to be a ternary prime number, where p is an odd number larger than 2. p0 will be equal to 3p, which is always divisible by 3. Second, p1 equals to 3p plus 1, where it is even when p is larger than 2, and hence divisible by 2. Lastly, p2 is equal to 3p plus 2, and p is odd when p is larger than 2. When p is 2, then the ternary number 21 is actually 7 in the decimal system. This is the case shown above. And after that, we prove that the length of every ternary Pn tree is finite also by Fermat's little theorem, and we have succeeded in both the binary and the ternary system. I will conclude by saying that, firstly, the Pn trees can classify all prime numbers in an elegant manner. Secondly, prime number trees show an identification to prime numbers. Thirdly, binary Pn trees and ternary Pn trees are finite in length. Lastly, prime numbers can be described in groups, like Pn trees, rather than just individuals. In our opinion, Pn tree will now allow a new perspective for mathematicians to view prime numbers not only as discrete individuals, but as branches in the trees and members in a family. We would like to thank you all for your precious time, because it has really been a fruitful experience and a valuable chance for us to share our thoughts on mathematics, and it has been a dream come true. So thank you once again.